All right, well, I don't want to bump things too long because we're going to take it out of our breaks probably. So let's actually get started. So Leah, you can share your screen, and while you're doing that, so Leah is from the University of Chicago, and we'll be talking about gravitational wave probes of parity violation. But before I spotlight you, I just want to remind people there is a Q&A box, so I encourage you to use that. But because we're in a regular Zoom meeting, you can totally raise your hand and ask questions that way as well. And I'm happy to call on you. You can ask your questions yourself at the end of the talk. The chat box should also work in this session. So if you want to make any comments or whatever in the chat, you can do that. If you find out that I think it's set that everyone can use the chat. If you check and find out that you can't, let me know. But I think that's the case, that everyone should be able to use the chat. All right, so given that, so Leah, it'll be 15 minutes plus 5 for question and answer, and I'll, if you're starting to get close, I'll make a noise or something so that you know you're getting close. And I will spotlight you. Go ahead and you can go ahead and get started.
Okay, great. Thanks so much. Yeah, thanks for the introduction and for everyone to be here. Again, I'm Leah Jenks, and I'm going to be talking about gravitational wave probes of parity violation. Can everyone see my mouse also?
Yep, you're all good.
Okay, great. Okay, so before I get into some of the more technical details of the talk, I just want to start with the main takeaways. So I'm mostly going to be focused on talking about a new theory agnostic approach, which parameterizes specifically propagation effects of gravitational waves in parity violating gravity. And then I'll also talk a little bit about applications of this parameterization to gravitational wave data, including the stochastic gravitational wave background, as well as the GW 170817 coincident gravitational wave electromagnetic event. And I should also say that everything I'm going to be talking about today is in collaboration with all of these very wonderful people listed here. Okay, so when we're talking about parity violating gravity, parity is obviously a very important symmetry in physics. And we can think of a parity transformation as some operator P, which acts on X. And this flips the sign of X and takes some coordinate system X to minus X. So if I act the parity operator on some function f of X and it returns just itself without a minus sign, I consider that function f of X to be parity invariant. Whereas if I act P on f of X and it comes back with a minus sign, then I take this to be parity violating. And so although parity symmetry is extremely important in the universe, it's also worth noting that the universe is asymmetric. So for example, the weak force is a great example of this. Handedness is important when it comes to couplings to the weak force. There is this asymmetry in the matter-antimatter distribution, the fact that there is much more matter. And then recently in cosmology, there have kind of been hints of parity violation in various observables, including in the CMB, as well as in the galaxy 4-point functions. I say hints because these types of measurements are obviously very difficult to do, and there is always, some back and forth on whether things have been confirmed or not. But more and more, it's appearing that this idea of parity violation may be more important, and specifically, these types of effects can arise from parity violating gravity. So when I'm talking about parity violating gravity, I'm specifically referring to modifications of general relativity or extensions of general relativity, which violate parity. So for example, kind of the generic way you might write down one of these theories is by the following action, where this S here is just the Einstein-Hilbert action, where K is 16 pi and R is the Ricci scalar, just the usual Einstein-Hilbert action of GR. And then some additional parity violating contribution to the action, which I won't specify, but generally it is some function of curvature invariance. So for example, the Ricci scalar or the Pontryagin invariant. as well as some auxiliary scalar field phi. These types of theories often propagate additional fields. So as I said, everything I'm going to be talking about in this talk is going to be kind of theory agnostic. I'm not going to specify to any particular theory, but certain examples of this include Chern-Simons gravity is probably the most prevalent. And so these types of modified gravity theories can have a wide variety of effects on gravitational and cosmological observables. So significant work has been done to study these effects in gravitational waves. These types of theories can modify black hole solutions as well and the behavior of black holes. They can have implications for the early universe, such as baryogenesis or leptogenesis. And then also, as I mentioned, can be have parity violating contributions to these galaxy endpoint functions, as I mentioned before. This is, of course, not an exhaustive list, but just to give you an example of the types of things that can be modified. So I'm specifically going to be talking about, as I said, parity violation in gravitational waves. And so there are two ways in which parity violation affects gravitational waves. So the first is a propagation effect. So if we consider a circularly polarized gravitational wave, as that wave propagates from its source to us here on Earth and our detectors, it can have two different types of effects. So one of these effects is amplitude birefringence. So this just means that the right and the left-handed polarization modes have their amplitudes evolving differently. In particular, one is amplified and one is attenuated. We can also have velocity birefringence, which just means that each of the modes is traveling at a different speed. We can also have generation effects in parity violating gravity that affect the generation of gravitational waves. This mostly arises from the fact that some auxiliary scalar field is extracting energy from the binary, and therefore the in-spiral dynamics are changed from what you would expect in GR, and this ends up being a modification in the in-spiral rate or the chirp rate, which enters at second post-Newtonian order. So for the rest of this talk, I'm just going to be focused on propagation effects. And then here you can see just kind of an example of some circularly polarized wave traveling through a birefringent medium to get kind of a sense of the types of effects we're thinking about. Okay, so you might wonder, why are we doing this? Our goal is to parameterize parity violating propagation effects for gravitational waves for a variety of reasons. So as I mentioned, parity violation, specifically parity violation in the gravitational sector, is kind of growing interest because of all these hints of parity violation in our observables that could potentially arise from the gravitational sector. But there's not been any sort of kind of systematic study of these types of effects for gravitational waves that map kind of towards many theories. So there have been some attempts to parameterize these types of effects from the theoretical side, but these don't necessarily translate in a convenient way to do data analysis. And on the other side, there has been work done to do data analysis on these types of theories, but using a parameterization that is not the most general to map back to theory. So our goal here is to come up with a theoretically motivated parameterization that maps to a parameterized post-Einsteinian or PPE waveform for a broad range of theories that can therefore be easily used for data analysis. Okay, so I quickly want to just go over some of the basics of gravitational waves in GR, which may, of course, be very familiar to this crowd. But we can consider a circularly polarized gravitational wave on an FRW background, which we can characterize in the following way, where here A is just the amplitude, RL just refers to right or left, eta is conformal time, phi is the gravitational wave phase, and then K is the co-moving wave number. And the right and left-handed modes obey the following propagation equation, where here H is just the co-moving Hubble parameter. So when we have modifications to GR, or these parity violating modifications, they end up arising essentially as corrections to the phase. And so we can have imaginary corrections to phi, which end up entering the waveform as an overall amplitude modification, as well as corrections to real corrections to the phase, which enter as an actual correction to the phase, which give us velocity modifications. Okay, so now I want to go over the parameterization. So I've shown here kind of this unwieldy equation, which is the modified propagation equation from the last slide, which now takes into account generic parity violating effects. So let's kind of go through this one term at a time. So here is just the usual GR term, which characterizes the amplitude. And then we have the second term here, which is the parity violating contribution that will lead to amplitude birefringence. So here, small lowercase lambda RL is just plus or minus 1. K is again the co-moving wave number. N is an odd integer. And then here alpha and beta are two parameters which kind of parameterize the specific parity violating effects. So this will be kind of theory dependent parameters. And then we also have this parameter lambda PV, where lambda is essentially the cutoff scale of the effective field theory. So we generally think about these types of theories in an EFT context, considering it to be some low energy limit of some high energy theory. So lambda is just the cutoff scale for that regime of validity, and then A is just the scale factor. So similarly, in the second term, which will lead to the velocity effects, we just have, again, the GR term, and then a term with a very similar form for the velocity contribution. So again, gamma and delta are the specific kind of theory-dependent parameters which control the amount of parity violation. And then notice also that here, M specifically is an even integer in this case. Okay, so this modified propagation equation leads to the following expression, the following modification for the right and left-handed polarization modes in the following way. So here H bar is just the GR value. This is normally what you would calculate in GR. And then we have these two additional contributions. So this contribution here, I'll just call delta phi A. And this is the overall amplitude coefficient, or the modification to the amplitude. And here we've defined these effective redshift and effective distance parameters in the following way. And we have also taken alpha and beta to be well approximated by their current present day values, which I'll talk a little bit more about in a second. And then we also have a velocity contribution birefringence, which I'll call delta phi V, which again has a very similar form here. So this is generally how gravitational waves are modified in a kind of generic parity violating theory. Okay, so I want to quickly discuss how we actually derived these expressions. So there are two approaches that one can take. The first is a theory approach, which is kind of a bottom-up approach, I like to say, which is to take a variety of parity violating gravity theories and calculate gravitational wave modifications in each theory, look together at all of the results, and then extrapolate backwards to kind of a generic, all-encompassing parameterization, which characterizes all of them.
Hey,
On the other hand,
you have about 2 minutes, by the way. Just
okay, thank you. On the other hand, we can take what we call a general approach, which is to begin with a generic modification of the propagation equations, and then use dimensional analysis and a small expansion from GR to identify the relevant terms and arrive at the parameterization. And so doing both of these approaches, they actually match and you arrive at the parameterization that I showed you before. So I quickly want to discuss some of the assumptions that go into this. The first is that deviations from GR are small, as I mentioned, that we are within the regime of validity for the effective field theory. We focus specifically on parity violating modifications. There are many other modified gravity theories, which include non-parity violating corrections, but these are more well studied, so we just focus on parity violation. We also assume that gravitational wavelengths are short in comparison to the expansion of the universe. And then we also assume that the evolution timescale of the parity violating parameters, this alpha, beta, gamma, and delta, are also long compared to the expansion of the universe and can be well approximated by their current day values. So I'll just show briefly kind of the mapping that we can do to a variety of theories. Not all of the parameters in the full sum appear. We just have these specific ones. And then I think for the purposes of time, I'll just be very brief here, but one can also show that this parameterization can be mapped to a parameterized post-Einsteinian waveform, which was first introduced to just generally parameterize deviations from GR and is very useful in a data analysis context. And there's a very simple mapping from our parameterization to a PPE waveform, which I'm very happy to answer more questions about. And then I'll also just mention that measuring these types of effects is very difficult because there are many degeneracies with waveform parameters, in particular the distance and inclination of the source, as well as the polarization angle. Again, happy to answer questions about that. And then lastly, I just really want to mention a few data applications that one can do with this type of parameterization. So because of these degeneracies that I mentioned, we can, it's been hypothesized that doing analysis with a coincident electromagnetic and gravitational wave event can break these degeneracies and allow for more precise constraints. So this is work in progress with GW 170817. We can also use the stochastic background. So in this case, I'm thinking about the LIGO stochastic background, which has not yet been detected, but there is analysis that can be done here. These two works should be out shortly, so please stay tuned. And then I'll also highlight some work by various groups which have done this type of analysis for binary black holes and have stacked detections from the full GWTC2 and GWTC3 catalogs to place constraints. So a lot of good data analysis applications for this. So with that, I think I am probably just about out of time. So I'll leave up my conclusions, and thank you so much for your time. And I'm very happy to take questions.
Great. Thank you very much, Leah. All right. Yeah, feel free to use the virtual hand claps. And I can, since I'm unmuted, I can give an actual hand clap. Are there any questions? I don't see anything in the Q&A box, but feel free, since we're in the Zoom meeting, to raise hand if you would like to ask any questions of any kind. And maybe while we're waiting for that, I will ask one. You mentioned that the measuring by refringence is hard because of all the covariances and stuff. Does this mainly show up in slight phase changes in the waveform that's showing up in the detectors? Is that really what the detailed measurement would be? Is just a slightly different phase offset effectively?
Yeah, so there's changes in the gravitational wave, both the amplitude and the phase. So for velocity birefringence, for example, if you have this is enters as a phase effect. So this is very degenerate with, for example, like the polarization angle, which is difficult to measure unless you have electromagnetic counterparts. For the amplitude effects, for example, this is degenerate with the distance and the inclination. So you might measure something that looks slightly off, but it could be, you have amplitude birefringence, or you've just measured the inclination of your binary, incorrectly, and you're seeing a slightly different waveform in that way. So it's both phase and amplitude.
Gotcha. Yeah, thanks. That helps a lot.
Thanks for the question.
Other questions? We have time for maybe one more. I'm not seeing any. All right. So let's see. While maybe we're potentially waiting for one more quick one. Purnima, maybe you can turn your camera on and start sharing your screen, and then if there's no more questions, we'll move on to Purnima's talk. Yeah, I still don't see anything. So thank you very much, Leah.
Thank you.
All right, so next up we have Purnima Narayan, who's from University of Mississippi here in the US. So go ahead, Purnima, and excuse my dog.
Hello, everybody. Am I audible? Okay. Okay, so my name is Purnima Narayan, and I am a PhD student at the University of Mississippi. I would like to present my work in front of you all today that I have been doing together with Dr. Nathan Johnson-McDaniel and Dr. Anuradha Gupta. And I have attached our archive link here and a QR code. So if you'd like to scan it or use this for reference while I'm talking, please feel free. So today I'll be talking about our recent paper that came out on arXiv, which is when can we ignore eccentricity when testing general relativity with gravitational waves. So let me give a quick introduction. Our motivation to do this study is that the theoretical studies predict that of the order 5% of all the dynamical mergers in globular clusters have eccentricity above 0.1 at 10 Hertz. So it may be possible that we have already detected binary black holes with non-negligible eccentricity and might detect even more with O4. However, the waveform models that have been employed in LVK's current tests of GR describe binaries on quasi-circular orbits, and thus eccentricity may appear as false deviations from GR. We are thus interested in knowing how an eccentric binary black hole signal would show up in some of the standard tests of GR that are carried out by LVK. So let me start with giving you some specifications of our injections. We consider SXS simulations and make non-spinning face-on injections. So by face-on, we would only want to focus on m is equal to 2 modes. That is, we are not looking at the contribution from higher order modes. The distance we place our binary at is 400 megaparsec, and we consider a total mass of 80 solar mass. So to the left, you can find a table of all the binaries that we consider. So what you can see here is that for each mass ratio, where we consider 3 mass ratio, Q is equal to 1, 2, and 3. For each mass ratios, we have one high eccentricity. For example, for Q is equal to 1, SXS 1357 is a high eccentricity signal. We consider a lower eccentricity one, for example, Q is equal to 11355. And we also consider a quasi-circular signal for each of the mass ratios for comparison. The values of eccentricity here are all given at 17 Hertz from PN comparison, and we have taken them from Hinder et al., except for the values that have upper bounds from eccentricity reduction. The selected distance of 400 megaparsec gives SNRs of about 120, 106, and 90 for the 3 mass ratios that we consider respectively, with the standard O4 forecast noise curves that we are using in our work. Along with these SNRs that is mentioned here, we also consider selected lower SNR cases for each mass ratio, and I would be talking more about them in some of the future slides. Now that we have gone over the injection specifications, let me go over some of the recovery specifications. So in our project, we are using 4 standard tests of GR, and 2 of them are parametrized tests, which is Tiger and FTI. So while Tiger and FTI are both parametrized tests in the sense that they introduce parametrized deviations to the phase of the signal, in Tiger, the model of Tiger is constructed such that the deviations in the PN coefficients, that is at lower frequencies, are allowed to extend to higher frequencies in the sense that they affect the late and spiral and merger ring down portions. And the waveform that we are using to recover for the Tiger test is the IMR phenom PV2, which only has the dominant 2 plus minus 2 modes. Whereas in FTI, the model was constructed in such a way that they only consider deviations in the PN coefficients, And the higher frequency deviations are tapered to 0. The model that we use for FTI is SEO BNR version 4, higher modes, ROM. And you can see that this includes higher order modes along with the dominant 2 plus or minus 2 modes. It has 2 plus minus 1, 3 plus minus 3, 4 plus minus 4, and 5 plus minus 5. And FTI can be applied to any aligned spin signals. So along with these 2 parameterized tests, we use 2 other tests. And one of them is the parameterized test of propagation effects. And that is the modified dispersion relation. That is, we'd like to see the propagation effects if we are modifying the dispersion relation in relative to GR. And the model that we use here to recover is IMR phenom XPHM, which also considers higher order modes in addition to 2 plus minus 2, which is 3 plus minus 3, 3 plus minus 2, and 4 plus minus 4. And finally, we use a consistency test, which is the InspiralMerger-Ringdown Consistency Test, where we would like to check the consistency with the inspiral and the post-inspiral parts of the signal and see if they are consistent with each other. And the model that we use to recover this is the IMR phenom XPHM. So we include the same mode content in the injections as in the recovery waveform. And since we are only considering the face-on injections, so since we only consider the face-on waveform, we are only including 2-2 and 3-2 modes for the IMR phenom XPHM, and just the 2-2 mode for others, since others would have no contribution from M is equal to 2 modes. Now that I've gone over the injection and recovery specifications, let me go over to the results. So this is a really busy looking plot. So let me break this down to you. The first horizontal row here is giving you the plots for Q is equal to 1. The central one is giving for Q is equal to 2, and the lowest one is for Q is equal to 3. The purple plots here are the quasi-circular plots. Green ones are the lower eccentricity, and the orange ones are higher eccentricity. So for each mass ratios, we would be plotting phi 0 to phi 7, which are the inspiral parameters, beta 2, beta 3, which are and alpha 2, alpha 3, alpha 4, which are the post-inspiral parameters. So let's see what are we able to infer from this busy looking plot. So we see here that all the purple plots are including GR, where the GR value is 0, where the deviations go to 0 within the 90% credible interval. And the high eccentricity signals exclude GR at well above the 90-degree credible level. That is greater than 3 sigma, except for some Q is equal to 2 cases. And I would go into the sigma plots in some of the future slides. We see that some of the lower eccentricity signals, that is the green ones, show moderate deviations. That is, some of them have greater than 3 sigma GR deviations, but most of them show less than 3 sigma, with some even less than 1 sigma deviations. Now, if you look at the black violins, which have only the outlined contour, so we see that there is 1 each for Q is equal to 1, Q is equal to 2, and Q is equal to 3. For example, the parameter beta 3 has a Q is equal to 1 low SNR plot. So the way we pick this signal is that we wanted to choose a distance for the signal such that the 90% credible level would touch 0, keeping the median same. And when we computed the scaling of all our violins, we picked the one which gave the maximum luminosity distance, and we chose the one with maximum luminosity distance for each mass ratio. So we wanted to see if, since we have considered such high SNR, we wanted to see if we scale the distance further and further away, and if we have a lower SNR, would the posterior still scale as we expected? And here we see that Q is equal to 1 is at a distance at 1.96 gigaparsec, Q is equal to 2 at 1.48 gigaparsec, and Q is equal to 3 at 1.52 gigaparsec. So we still see that the lower SNR cases are showing GR deviations at 90% credibility. Another important findings that we had is that if you look at the deviations for each mass ratio, they are depending on the sign, or so the sign of the deviations is changing with the mass ratio. For example, if we look at phi 0, for Q is equal to 1, the deviations are negative. For Q is equal to 2, the deviations are negative. For Q is equal to 3, the deviations are positive. So there is some relation here that we investigated, but we did not see any correlation for these sign dependencies on the PN parameters. So this is the results from the Tiger test. Let me proceed to the FTI test. So again, we have the similar structure. The first row is Q is equal to 1, then Q is equal to 2, and Q is equal to 3, and the colors remain the same. So again, we observe that all the quasi-circular violence are including GR within the 90% credible interval. The high eccentricity signals for Q is equal to 1 and Q is equal to 3 show a high deviation that is greater than 2 sigma with some even greater than 3 sigma. Whereas Q is equal to 2 high eccentricity signals show at most moderate deviations, which are about less than similar to 2 sigma. And the reason this is that eccentricity effects and the dephasing parameter effects are orthogonal to each other. Again, here we have 3 low SNR plots. That is, for Q is equal to 1, we have it for phi 1. For Q is equal to 2, we have it for phi 7. And for Q is equal to 3, we have it for phi 0. And if you see here that the parameters here are only the in-spiral parameters, there is no deviations in the post-in-spiral parameters, as I explained for the FTI test. So here we observe that the low SNR case for Q is equal to 1 and Q is equal to 2 are scaling as expected, whereas Q is equal to 3 is shifted beyond 90 degrees. And all the low SNR cases show about moderate deviations for Q is equal to 1, 2, and 3. That is, all of them are below 2 sigma. So this is for FTI. Let us move on to the results from the modified dispersion relation test. So here we are plotting the parameters, which is A alpha versus alpha. And we see, again, the structure is the same. This is Q is equal to 1, 2, and 3. And the purple ones are for quasi-circular, green ones are for low eccentricity, and orange ones are for higher eccentricity. What we observe here is that the higher and lower eccentricity signals show small deviations for Q is equal to 1, 2, and 3. That is, all of them are less than 2.5 sigma. And this can be attributed to the eccentricity and dephasing parameter having orthogonal effects, again, similar to what we observed in Q is equal to 2 FTI. However, there are some exceptions, which is Q is equal to 1, alpha is equal to 1.5 lower eccentricity case, which is having a deviation higher than 2 sigma. And the Q is equal to 3, alpha is equal to 3 higher eccentricity case, which is about 3 sigma. And I would be showing a comparison of all the sigma values in one of the later plots. So that will be easier for you all to compare between the different tests. Here we see that the low SNR plot, which is the black outlined for Q is equal to 1 and Q is equal to 3 are also scaling as expected. Whereas the Q is equal to 1 is at 0.76 gigaparsec and Q is equal to 3 is about 0.52 gigaparsec. So the SNRs that we got for the low SNR cases are about the level of 15 to 20 for Tiger and a little bit higher, around 40 to 50 for FTI and MDR. The Q is equal to 2. Lowest in our case is still under analysis. It's in progress. So now that we finished the 3 parameterized tests, we have made a plot of comparison of all the Gaussian sigma values for the lower eccentricity, higher eccentricity, and comparing them for all mass ratios. So here, as you see, we can see these upward facing arrows. And these upward facing arrows are showing the lower bound, which is found to be 3 sigma. And this lower bound is due to the uncertainties due to finite number of posterior samples. That is, the results above 3 sigma cannot be said confidently.
Hey, Purnima, you should try to wrap up in a minute or 2 if you can.
Okay. So we see that in the most high eccentricity cases lead to GR deviations higher than 3 sigma in Tiger, and the low eccentricity signals show GR deviations greater than 3 sigma. Similar observations are seen for FDI, except for Q is equal to 2. And all MDR cases are excluding GR at less than 3 sigma. Then we come to the IMR-CD test, where we see that the high eccentricity and the low eccentricity signals show significant inconsistencies for Q is equal to 2 and Q is equal to 3. That is, they are not encompassing the 0 value. And not only in the eccentricity, we also see biases in the quasi-circular cases, which can be attributed to the inclusion of higher order modes. And through an ongoing study by Mukesh et al. From ICTS, we see that these large biases are only observed for binaries, which are very close to face-on or face-off. Thus, for comparison, we made plots to show only the 2-2 modes. And we see that the higher eccentricity still show inconsistency, whereas the lower eccentricity and the quasi-circular are consistent with GR within the 90%. So summarizing the IMR-CD results is that significant biases are only seen in signals close to face-on or face-off. And with the inclusion of higher order modes, we see significant GR deviations for Qs of 2 and 3. Without inclusion, we see that quasi-circular are consistent, and we still find GR deviations for the higher eccentric cases. So finally, to summarize the work, we performed 4 standard tests of GR on quasi-circular and eccentric non-spinning NR waveforms. And we saw that eccentricity effects did show up in all the tests of GR we considered. And thus, it will be necessary to exclude the possibility of an eccentric binary in order to make any claim about detecting a deviation from GR. With that, we are planning to extend this work to look at the response of other effects like lensing and the presence of a third body on the test of GR. Thank you for your attention.
Great, thank you very much, Purnima. We have time for a question or 2. I don't see anything in the Q&A box. Feel free to type a question in there if you want, or raise a hand. And I think I see a hand. Leah, you can go ahead and ask your question.
Yeah, thanks for the really interesting talk. I just had a question about, so if you were to make an observation of something that looked like a deviation from GR, is there a way currently that you would be able to disentangle it? I know there's not any waveforms that, as far as I know, take into account eccentricity, but is there a method that you would use to like be confident about whether what you're seeing is actually a deviation from GR or just an eccentric binary?
Well, currently we would not be able to do that because eccentric binaries are formed in dynamical environments where precession is also an important part of the signal. And currently we see that there is a degeneracy between eccentricity and precession. So it would be a little difficult to disentangle. So if we would have eccentric models, and then if we are able to match eccentric injections with eccentric models, then we would get some hints to be more confidently able to say if the observed signals are indeed eccentric or are more of the GR deviations.
Thank you.
All right, I don't see any other questions and we're running low on time. So I'm gonna give it a second. Yeah, we should probably move on. So thank you very much, Purnima, for your
Thank
really
you.
nice talk. And next we have Anuj Mishra. Anuj, you want to unmute and make sure we can hear you talk and then share your screen?
Okay.
Right. Yeah, so Anuj is talking about eccentricity versus microlensing, the effect of ignoring eccentricity in microlensing in microlens signals. Well, actually looks like the title changed a bit there. I was reading it off the schedule. And Anuj is from IUCAA in Pune, India. So go ahead, Anuj, and I'll give you a 2-minute warning.
Thanks, Scott. So I'm Anuj. I'm a PhD student at IUCAA Pune. And as Scott mentioned, I'll be talking about the interplay between eccentricity and microlensing. And I'm happy to present this talk right after Purnima's talk because that talk sets a nice foundation for eccentricity and its effect on gravitational waves, and also because we used their injections in our study as well. So thank you for that. So for the purpose of this talk, microlensing just refers to gravitational, the wave effects in gravitational lensing of gravitational waves. And we know that microlensing and eccentricity are two independent physical effects that have not yet been observed in the real GW data with high confidence. So, for example, microlensing can be used to constrain the population of compact dark matter fraction. Compact dark matter objects, which can be be a fraction of dark matter, and eccentricity, as Purnima mentioned, can help us also shed light on the formation channels of a binary. So that's why these two effects are important to disentangle. So currently, we do not have a good idea of the rate of microlens signals, but we know that for eccentricity, as we probe early stages of a binary evolution, or as the sensitivity of the detectors themselves improve, the presence of eccentricity will become important. So especially with future detectors, third generation detectors like Cosmic Explorer and Einstein Telescope, and space-based detectors like TESIGO, it will be important. So we did this work from the perspective of microlensing searches. So the methodology that is currently being employed to search for microlensing, how that can be biased due to the presence of eccentricity. So so here I'm again giving a rough overview of what microlensing is. So you have a source and you have an intervening microlens. If it is an isolated point lens, then if its mass is in the range of 10 to 10 to 4 or 10 to 5 solar masses, then what happens is that the micro images or images that this microlens produces are unresolved. And in those cases, one can no longer work with ray optics. One has to take wave effects into account, and it leads to interference pattern. So it's just like when we have light and light in a double slit experiment, and if the wavelength of the light is comparable to the width of the slit, then wave effects come into picture. So in simple words, for gravitational waves, if the wavelength of your signal is comparable to the Schwarzschild radius of the lens, then wave effects come into picture. And it leads to frequency modulation of your signal, which is encoded in this amplification factor denoted as f of f, and which is multiplied by your unlensed waveform in the frequency domain to get the microlensed waveform. Sorry, I'm missing f dependence here. So as an example here, I'm showing what kind of modulations we get in microlensing. So here I fixed a mass to be a redshifted lens mass to be 100 solar mass. So for a point lens, it depends only on two parameters, the mass and the impact parameter. So the impact parameter is just the distance between lens and the source in dimensionless units of, say, Einstein angle. So here I fixed the mass to be 100 solar mass, and I'm, say, varying a different y, and I'm getting these kind of modulations in the absolute and the phase part of f of f. So as we can see, for the lower values of y, we have very strong modulations, but also these are very slowly varying. Whereas for y equal to 3, the modulations are very weak, but they are like highly oscillating, like there are more cycles of modulation. So these kind of effects happen as we change Microlens parameters, and if we change mass, these modulations come earlier in the frequency. So to start with, we started with some NR injections, full IMR eccentric injections, which was provided gladly by the group at University of Mississippi. The talk that Purnima gave for me, and these are the rough values that were used. The eccentricity was around 0.1, defined at f equal to 17 hertz. The SNR of this different signals was roughly 100, and the total mass was 80 solar mass, and for 3 mass ratios. So what we did is for these injections, we computed the base factor for the microlensed hypothesis and the unlensed hypothesis. And in the microlensed hypothesis, we have just additional 2 parameters than the usual parameter estimation that we use, or waveform model that we use for BBH. So, so what we notice is that for all the quasi-circular cases, we do not get any preference for microlensing as what we should expect. But for all the eccentric injections, we get strong to very strong support for microlensed hypothesis. So this is very interesting to see. And also, if one sees the posteriors for microlens parameters, they are very well recovered. So, for example, for non-eccentric injections, the prior and the posteriors are almost same, and the mass that we get is peaking at very low mass, which is not interesting at all. And whereas for eccentric injections, the mass is significant, and also the convergence on the posterior of Y is pretty different from the prior that we gave as input. So, which is also encoded in the Jensen-Shannon divergence values. So, for all the quasi-circular cases, if we calculate this value between prior and posterior, we get value less than 0.1, which basically says that the posterior is not very informative, whereas for all the eccentric injections, we have this value greater or equal to 0.5, which says that these are quite informative in the case of eccentric injections. Then we also did some eccentric injections using TUB-RSMS waveform model, where we considered non-spinning zero noise injections and fixed eccentric SNR of 30. And we defined eccentricity at a dimensionless frequency of about this value, which corresponds to 10 hertz for a 60 solar mass binary. And we did that so that we are defining eccentricity at the same point in the evolution of a binary. And so here in the plot, I am plotting this base factor for the recovery of Microlens versus unlens in log10 scale versus eccentricity for different total mass and mass ratio that I considered. And one can see that as one increases eccentricity, the preference for Microlens hypothesis drastically increases and almost monotonically increases, except for this exception here, where it decreases a bit and then increases. And also another thing to notice is that for any case where the Microlens hypothesis is being favored, it is favoring more the smaller, the lighter binary. So for example, the red one, 30 solar mass, is being favored more for microlensing than the 60 and then the 90. And so is the trend here as well. And if we see the posterior, then again, we see that they are quite well recovered in the Microlens parameter space for eccentric injections, whereas for non-eccentric injections, they are just mostly returning the prior for Y, and for mass, they are peaking at very low value. And again, for eccentric injections, the impact parameters for example, in this case, we are getting is peaking at very low values, which astrophysically are very improbable. And then lastly, we also did some population study, again using QBT-SNS waveform model. We generated GWTC3-like population of around 20,000 eccentric signals. And we took the usual threshold that we take of 8, and PSD that we used is 0 target sensitivity. And again, we defined eccentricity like before at this value. And the range of eccentricity that we considered is 0.01 to 0.5. And what we calculated is, then what we did is we computed fitting factor for both the models, assuming microlensed templates and unlensed templates. And for example, compared the two, which the injections like to get the information of which template is being preferred more for these eccentric injections. And what we find is that, as you can see, most in most of the plot, the markers are blue color, so which represents that microlens template is being favored more for these eccentric injections over the unlensed templates. And for example, for above eccentricity 0.2, there are hardly any red points. And this is expected because in microlens templates, as I said earlier, we have 2 additional parameters. So when we introduce any additional parameter in our model, so the goodness of fit always improves, but that does not guarantee that our model will also be favored if we do nested sampling. But we saw previously that this preference is strong enough to even favor to even become as a preferred model in the model comparison. And from this population study, we also noticed a slight correlation with the total mass of the binary for the favor of Microlens hypothesis. So for a given eccentricity, if we have lower binary mass, then the microlens template will be able to fit it better. That means if you have more cycles of eccentric, we have more eccentric cycles, then microlensing will be able to be even more preferred over the unlensed signals. And lastly, if we plot the distribution of the best fit microlens parameters in our population, coming from fitting factor analysis. So although I do not trust the parameter values that are coming from fitting factor analysis, but in this case, if I just plot them, then this microlens mass distribution that I get looks kind of informative, and also it makes sense that it is peaking at around this value. And if we notice all the parameter estimation recoveries that we did, the mass actually peaked at around this value. For example, you can see here it is peaking around 2.5 here as well, and here as well. So in fact, we notice in most of our cases that is indeed the case. So right now we do not have any physical explanation why it is favoring a particular lens mass, but we will soon have an answer to this. Whereas I don't see any useful information that for why here from this population study. So I'll just conclude. So our main conclusion is that eccentricity seems to be highly degenerate with microlensing, and our analysis shows that the preference for microlensing improves or increases with as the eccentricity increases, or if the eccentric number of cycles increases, or if the SNR increases. And we saw some very strong preference for microlensing in some of the cases, which suggests that there is large degeneracy, and goodness of which also suggests that microlens templates are almost always preferred over unlensed templates. And one interesting thing that we observed is that currently in microlensing searches that the collaboration, LIGO collaboration is doing, they use prior from 0.1 to 3, because a value less than 0.1 is very astrophysically improbable. But we saw because of eccentricity, if you are recovering using Microlens templates, we can even get values in this range. And lastly, to explicitly show that the effects are quite degenerate, we also need to recover using eccentric waveform model, which we are doing right now, and some runs are ongoing. So that will help us understand more how degenerate these two effects are. And obviously, we will extend this study to for future detectors, where role of eccentricity will be much more important. So thank you. I'll just stop here.
Great. Thank you very much, Anuj. All right, let me get to the other view here. All right, perfect. Yeah, thank you very much. And applause from the audience. Thank you. I don't see any questions in the question and answer box. Feel free to raise your hand. We definitely have several minutes for questions if you would like. I actually have one question that kind of a higher level question about microlensing in general, and that is for do we know for the next upcoming runs, has there been, I'm sure the estimates are wildly have amazingly large ranges, but are there estimates as to what the expectations might be to see a microlensed event?
That's a very good question, but we do not have any understanding of microlensing. So what we instead do is we anyway try to search for microlensing signatures in all the events, and the non-detection of microlensing we use as a constraint on the population of compact dark matter. But because we don't have much idea about the population of compact dark matter, we cannot like say what will be the expected.
Gotcha. Thank you. Any other questions? Well, all right, we will end right now for this first section of the first section of this split session. I'm sure people have noticed that the session is split because the way Oxford Abstracts does things around 0 UTC. There's one more talk in the session, but we're going to take a 10-minute break first. So we will come back at basically almost exactly 10 minutes from now. It's 1 minute after the hour right now. We'll start again at 11 after the hour. We'll have one more talk, and then there's an empty talk slot, so there'll be a slightly extended break, and then we'll start at 0 hours UTC for the next after that. So we'll see everyone back here in about 10 minutes. Thank you. But meanwhile, I would like to check the next speaker just to make sure that we can talk. So I think that's Nami. All right, great. Well, welcome back, everyone. So our next speaker in this part of the session is Nami Uchikata from University of Tokyo and ICRR. And we'll be talking about searching for gravitational wave echo signals from the O3 events. So Nami, I'll give you a 2-minute warning if you're getting close. Take it away.
Thank you. I'm Nami Uchikata from ICRR, the University of Tokyo. I'm going to talk about a search for gravitational wave echo signals. So far, 90 gravitational wave signals were observed by LIGO, Virgo, and collaborations from 3 observing runs. And we think that these signals are originated from black holes or neutron star mergers. But it is interesting to consider whether there is any possibility of other compact objects. So in this study, we focus on this possibility and search for possible sequences of pulse-like signals after the compact binary coalescence. So this is a simulated waveform, and this is the binary black hole merger waveform, and usually we only analyze around this data. But in this study, we analyze the later part of the merger signals to search for the so-called echo signals. A possible source objects for echo signals are theoretical compact object models, such as boson stars, gravity stars, wormholes. The key features are the existence of unstable photon orbits and the absence of the event horizon. And this is a schematic diagram of radius and time. So after the merger, the signal is emitted to infinity, and we observe this as BBH signal. But a part of this signal falls into the object, and if the event horizon is absent, and then this signal will be reflected at the surface and emitted to infinity again. And part of this signal is again reflected at the potential barrier and falls into the compact object. And this happens iteratively, so we might observe additional signals after this BBH signal. And the interval is characterized by delta D echo, and this corresponds to the distance from the surface to the potential barrier. And roughly 1 second for heavy BBH and less than 0.1 seconds for light BBH. So if we can observe these signals, then this might be a proof for the modification of the classical horizon. Here I summarize previous studies on template-based searches. So far, various models for echo signals are proposed, but I listed representative studies that are used for the data analysis. So the first model is just a simply modeled one, and the evidence is reported from O1 events using this model. And later, other studies show loss significance using the same model from O1, O2, and O3A events. And in our previous study, we used a physical model that includes a black hole perturbation effect. And we show that the significance is low for O1 and O2 events using this physical model. And recently, a model motivated by Hawking radiation is proposed, and it is reported that base factor of 7 for echo signals for the GW19 or 521. And so in our previous study, we showed that we haven't found any significant echo signals. But when we use this simple model, that we have found that 5 out of 9 events have p-values smaller than 0.1. So if we assume that the data consistent with noise, then we expect that we get this p-value distribution is uniform. So it seems that this result contradict with the null hypothesis. So it is important to analyze more events to evaluate the significance statistically, since O1, O2 has only 9 events. So in this study, we search for echo signals for all 3 events. So again, in this study, we search for echo signals in all 3 events using 2 templates. One is originally proposed by Abedi et al. He called this the simple model. And the second is the physical model, includes a black hole perturbation event. We call this the BHP model. And we evaluate the significance by p-values for each event and check the distributions of p-values. And here we assume that the spacetime is curved with a modification in the vicinity of the horizon. So the spacetime is characterized by mass and spin of the remnant object. And also we assume the perfect reflection of the surface of the object. This is the exact form of the template model used in our study. So echo signals are based on cutoff InspiralMerger-Ringdown waveform, this part. And F is the reflection rate, and delta T echo is the interval of each echo, and phi is the phase shift. for each reflection. And for the simple model, we assume that this reflection rate is constant, and the phase shift is fixed to pi. In this case, we search for two parameters: a constant reflection rate and the time interval of each echo. This delta T echo can be calculated theoretically from remnant spin and mass. And for the second model, the black hole perturbation effect is included. And in this case, the reflection rate is frequency dependent and also depends on the spin and mass. So in this case, we search for three parameters: spin, mass, and also overall phase shift. We assume this is as a constant. And also for the first model, we fix the initial phase to 0, but in the second model, we also optimize the initial phase. And the number of echoes depends on the length of delta T echo. This is examples for best fit templates for GW190412. The left figure shows the reflection rate for the BHP model. So we can see that the frequency lower than 400 Hertz show very high reflection rates. That this means that these lower frequency signals cannot emit in infinity. The right figure shows the spectrum for two template models and the detector sensitivity for Hanford and Livingstone. So we can again see a clear difference in two waveform models. That for this BHP model, the lower frequency is strongly suppressed and the frequency band is narrow compared to the simple one. Next, I will explain the analysis method. So we first search for possible echo signals by analyzing the data after each event. So we already know the merger time, and delta T echoes can be calculated theoretically. So we only search for this specific time defined by delta T echo with some errors. So in this small interval, we compute how much filter, we calculate much filter XNR defined in this equation and search for the maximum SNR in this region. So we call this ball event. And after that, we also compute the background noise event. So we first search for echo signals after this delta T echo after the merger time. And so for several echoes time after the merger time, we take 1,000 segments with the same interval used for the search for this one. And in each background segment, you again compute the maximum SNR. And this is the rho BG. And count the number when this rho BG is the same or exceed the rho event. And by calculating this ratio, then we can get the p-value. And the larger p-value means that this SNR given by this part frequently occurred in the background segment. So this larger p-value means that this signal is likely to be noise. And for events and data, we select all three events with false alarm rate less than 1 per 1,000 here. This is the same threshold used in the LVK testing GR papers. And we also select events that are observed by both Livingstone and Hanford. All the data are from GW Open Science Center, the public data. And we choose the data length of 32 or 64 seconds for each event. But this depends on the length of delta T echo. And we use the Welch's method to estimate the detectors per spectrum density. And here, Kagura algorithmic library is partly used in this analysis. Also, this is the results of distribution of p-value. So this is a cumulative fraction of events against p-value. The diagonal line is from the uniform distribution. So this diagonal line corresponds to the null hypothesis. The data only contain noise. And this blue curve and orange one for simple model and BHP model, respectively. And this shaded region corresponds to the 90% error regions. So we can see that within this error region that both distributions are consistent, agreed with this diagonal line. So we have not found any significant echo signals from all three events. And here I listed the event that gives the smallest p-value. For the simple model, the smallest p-value is 0.027. This is given by GW20 or 311. And for BHP model, the smallest p-value is 0.044 by GW19 or 602. So we can see that different models gives a different significance. And let me comment on the GW19 0521. So from the recent study, exceptional significance is reported for GW19 0521. And the p-values for this event from our results are following. That the value is different due to the models, but we don't see much high significance for this event. Since the models are different in our study in this ability study, so yeah, it is surprising that the results are different when models are different. And also, our models are based on the merger-Ringdown waveform, so it is natural to think that echo SNR is proportional to merger SNR. So from this point, our results are reasonable since this event is not so high SNR event in all three. And the largest SNR event was GW2001 at 29, and the p-values are 0.08 for the simple model and 0.65 for the BHP model. So these values are larger than the smallest p-value I showed in the previous slides. And so yeah, our results show that the largest SNR PVH event does not give us strong significance for echo signals. So also from this point, we have not found any echo signals in all three events. In summary, we have analyzed gravitational wave echo signals from all three events using two templates. One is the simple model. This is just a repetition of the same waveform. And the second model is the BHP model. This includes black hole perturbation effects, and this model suppresses lower frequency signals. And by the p-value distributions that we have found out, the results are consistent with the null hypothesis. So we can conclude that there's no evidence for echo signals modeled by these two models. That's all. Thank you.
Great. Thank you very much, Nami. That was a really nice talk. applause from the audience. I'm looking, I don't see anything in the question and answer box. Feel free to raise your hand if you have a question. And I actually do have a question. So I noticed you're one of the things that you searched over for the echoes was the number of echoes that you're going to see. So it's kind of a two-part question. Number one is, theoretically, is there, how do the echoes decay with time? Do we know how they decay with time? And related to that, then, how do you know, how many echoes to search for?
They are actually model dependent. So for this first model, we assume that the reflection rate is, decay rate is constant. So yeah, we also search for this parameter. So this is a free parameter. And for the second model, this is determined by spin and mass. This is given by black hole perturbation. So in the second model, the decay rate is actually defined theoretically. And for the number of echoes, this is actually arbitrary. We don't have much. We can analyze with many not echoes, but in that case, we need a long data and the computational cost will be high.
Right, but I think my question is about that last line there about the number of echoes. Does each echo decrease in amplitude based on the models?
Yes. Yeah.
I mean, does the amplitude decay as each echo comes in?
Yeah. So the amplitude is actually decreasing.
Okay. And that must be model dependent, depending on the type of compact star. Gotcha.
Yeah.
All right, thank you. Any other questions? All right, well, thank you very much, Nami. It was very interesting. All right, so that ends this first part of the testing GR part of this session. So there's 2 more talks that will start at 0 hours UTC. So that's in roughly 1/2 hour from now. So feel free to take a break and we'll be back at midnight UTC. And I'll see you all soon. So it's about time to begin. So welcome everyone to the last part of the session for testing general relativity and some other related things with gravitational waves. So we have 2 talks in this session. So this will be about 40 minutes in duration in total. The first talk is by Sakshi Madekar from the Indian Institute of Science Education and Research in India. And Sakshi, you'll have 15 minutes, and I'll give you, if you're getting close to the 15 minutes, I'll give you a 2-minute warning vocally, and then we'll move on after that. All right,
yeah.
Ready to go?
Yeah.
All right, I'll take it away, Sakshi, it's all you.
Yeah, so thank you for the introduction. So once again, hello everyone. Myself Sakshi Satish Madekar. So I'm from IISER Mohali. So today I'm going to talk about testing general relativity with the gravitational waves using InspiralMerger-Ringdown Consistency Test. This work is done in collaboration with Nathan and Anuradha from the University of Mississippi. So I will start with the screen is stuck. Yeah. So why we need to test general relativity with the gravitational waves? So we know that black holes are the primary examples of strong field regime where the gravitational field is extremely intense. The reason for testing general relativity in the strong field regime is that it is the regime where the predictions of GR differ significantly from the predictions of the classical theories, which are in the weak field regime. So a variety of tests are applied to LIGO-Virgo detection. and the observation revealed no inconsistency with GR. So in the LVK organization or the LIGO Virgo collaboration, we have like various tests. So mostly here I will talk about the theory agnostic test or the null test. So it does not rely on the predictions of any modified gravity theories, but it reports deviations away from GR. So we will see three different tests for the study. That is the InspiralMerger-Ringdown Consistency Test, Parameterized Test, and the Modified Dispersion Relation. So we use Bayesian inference for all these tests to obtain the posterior distributions. So let's start with the InspiralMerger-Ringdown Consistency Test. I will go introduce them one by one. So first is the IMR consistency test. So we first estimate the initial mass and the spin from the inspiral, the low frequency part of the signal. And then we find out the final mass and the spin using some numerical relativity techniques. Next, we estimate the same parameters, that is the final mass and the spin from the merger ring down the low frequency part of the signal. And then we compare the two independent estimates. So we check the consistency by finding the fractional difference between the two estimates of the remnant mass and the spin. So this is the fractional deviation in the final mass and the fractional deviation in the final spin. In the right, we can see a posterior distribution plot. So this are the 1D probability distributions for the deviation parameters of the masses and the spin. So if we map over these, we get a 2D contour plot. And if we have these deviation parameters, the fractional deviation parameters to be 0 and 0, then we have, then this is for GR, and for this we have the plus sign. So we can see the contours surrounding the plus sign. So this is for a GR signal. So like this, we obtain many of the posterior distributions. Next is the parameterized test. So the gravitational waveform in the frequency domain is given by h of f, and we have the amplitude and the frequency, amplitude and the phase in the frequency domain. So phi of f is the structure of the post-Newtonian phasing formula in the frequency domain. This is the expansion of the V by C, where we have a series of V to the power k. So this phi k and phi kl are the post-Newtonian terms at different post-Newtonian orders. Also, we got the logarithmic terms at different PN orders, that is 2.5 and 3 PN. We have the velocity and the masses respectively. So here what this k corresponds to different PN orders. So for it ranges from 0 to 7. So if k is equal to 4, this means 2 PN order, k is equal to 5 means 2.5 PN order, and so on. So we introduce the deviation. For example, this is phi k. So we will have a deviation called as del phi k. So this is the equation how we introduce the deviation, the coefficient describing the GR waveform. So we have like two varieties of the parameterized test. That is the Tiger test, test infrastructure for general relativity, and the FTI, the flexible theory independent. So it uses a specific waveform and modifies both the post-Newtonian coefficient in the inspiral and the post-inspiral part. But this is not tied to any specific waveform and only consider the post-Newtonian coefficients in the inspiral part. So it allows deviation in the inspiral to affect the post-inspiral, whereas it tapers the deviation to 0 above a certain frequency. The third is the modified dispersion relation. So the propagation of gravitational waves in GR is characterized by a dispersion, by a non-dispersive behavior, meaning that the velocity of gravitational wave is independent of their frequency. So however, we can consider a more general dispersion relation. So we know that in GR, E square is equal to P square C square. So we introduce a modification. This A alpha is the dispersion amplitude, and alpha is the dimensionless constant. So if alpha is equal to 0, A naught greater than 0, we have a massive graviton with mass mg is equal to this. So this modification accounts for the propagation effect. And if we see that the gravitational wave is generated by the source, which is in consistence with GR, then all this deviation is because of the modification, that is the propagation of gravitational waves. So, so the talk which is based on meta-MRCT, I will introduce that test. That is the Meta-InspiralMerger-Ringdown Consistency Test. So it is so this test is based on the original IMR consistency test. So it is a method for comparing different tests, and this means that it accounts for a new test. Unlike the IMR-CT, where we split the signal, here we consider results from 2 different tests, and then we make a pair of it, and then we compare its result. So for example, we have a full binary black hole signal. So then from that, from one test, we will take the final mass and the spin. Similarly, from another test, we will have the final mass and the spin, and we will check the consistency of the estimates using this dimensionless fractional deviation. As already mentioned over here, that we use the same deviation parameters as the IMR-CT. So this is the fractional deviation in the mass and this spin for 2 different tests. So we use a summary TGR and executable of T summary to compute this deviation parameters. So we will see like why we need to consider a new test. So Johnson-McDaniel et al. Found out that the posteriors on the final mass and the spin are disjoint for different tests. So this is effective one-body waveform, which is in accordance with GR. And this is a simulated observation with larger GR deviation for the Tiger test. So we can see that the contours are too much disjoint. So hence we introduced meta-MRCT, and we can compare the recovery of the final mass and the spin between 2 different tests. So what all signals we consider to apply this test to? So that is the cause circular signal with phenomenological deviations from GR, numerical relativity signals, both cause circular and eccentric, and real GW events. So now we will see step by step how this test is been used to analyze the results. So we first compute the 2D GR quantile for meta-MRCT, that is for a pair of tests. So GR quantile is the quantile of the posterior distribution at which the GR value is recovered. So 2D GR quantile, 2D GR quantile means smaller value, means it is inconsistent with GR. So when it goes higher, it shows deviations from GR. So from the we got some GR quantile from the individual test with that will be the 1D GR quantile, and then we will compute the 2D GR quantile, and then we will compare the 2D GR quantile of meta-MRCT with individual test. So if we expect GR deviation and meta-MRCT is having a larger GR quantile, then it means that meta-MRCT is performing better than the individual test. So as I already explained, that this are the 1D probability distribution, and that mapping we got a 2D contour plot for the deviation parameters. So this is for one of the pair, that is the FTI D54 and the general relativity parameter estimation. For these both pair have been taken, and we got a GR quantile, and this is for an individual test GR quantile. So this means that meta-MRCT is having a lower GR quantile. This means it is in accordance with the GR waveform, which we are considering. So like this, we as this is for a single pair, we have like this 55 pairs, and we made a contour plot of them, a combined contour plot, and we can see that this is for a GR injection. So we have like 0 cases where meta-MRCT is performing better, and we have a median GR quantile of 2.9 with a upper and a lower bound. 2.9 means a smaller GR quantile. This means this is in consistency with the GR waveform. Next, we will see some non-GR injections, some smaller deviations and the larger deviation. So for smaller deviation, we cannot see any of the colored region, but here we can see some colored region. So why are these? So here we have like 36 pair and 55 pairs because of differences in the parameters considered for different tests. So by taking the combination, we got these numbers. And we can see that there are 0 cases for this and 2 cases where meta-MRCT is performing better. And we have a median GR quantile to be 12.7 for the smaller deviation and 99.6 for the larger deviation. And these are the lower and the upper bounds for the same. So this 2 cases here means that meta-MRCT is giving a larger GR quantile than the individual test. Plus, we have also set a threshold of 90% and above. This means that these 2 cases are there where meta-MRCT is performing better and also having a GR quantile of 90%. So this means that meta-MRCT can pick up GR deviations. Next, you will see eccentric simulation. So current waveforms consider only quasi-circular orbit. So a signal from an eccentric binary will be seen as a deviation. So we apply meta-MRCT to numerically simulated eccentric signals. These are the properties of the signal. We got redshifted mass to be 80 solar masses, luminosity distance to be 400 megaparsec, and eccentricity at 17 hertz frequency. So these all properties are there, and we have used the results from Narayan et al. For the study. You can also refer to Purnima Narayan's talk. So quickly moving on towards the result. So for mass ratio P is equal to 3. This is for a quasi-circular signal. This is for a lower eccentricity, and this is for a higher eccentricity. So quasi-circular signal means eccentricity to be 0. So we cannot see any of the colored regions, and this means that this is in accordance with the GR waveform which we consider. But here for lower eccentricity, we can see that meta-MRCT is performing better, and we can see some colored region. But here we cannot see any of the cases where meta-MRCT is performing better than the individual test. But what happens over here is, though the eccentricity is high and we cannot see some colored region, this is because meta-MRCT and individual test both picks up GR deviation for many of the cases to be 100%. So we haven't shown that in the colored thing because both meta-MRCT and individual test picks up GR deviations. Like last is the real event GW170817. So the signal was likely produced by a binary neutron star. So we can use the same BBH fit to compute the final mass and the spin as we use for the BBH signal. These fits are used to map the initial mass and the spin parameters to a 2-dimensional space. So for the parameterized test, these are the results, and we can see some tighter constraints over here. Let's see how meta-MRCT is behaving. So using parameterized test, we can see that this is not showing any violation from GR. So this is the contour plot for the GW170817 real event, and so we can see this number, that is 210. This are the pair of tests which have been made, and we can see that there are 0 cases where a meta-MRCT is performing better, and we got a GR quantile, a median GR quantile of 4.2 with a lower and an upper 90% down. So smaller GR quantile means it is in consistence with GR. So like I will summarize my work. So we proposed a new test of GR, that is meta-MRCT, which checks the consistency between 2 different tests. We examined its performance by applying it to some simulated injections. We also checked it for eccentric co-circular and some real GW events. So meta-MRCT finds deviations from GR like other tests. In some cases, meta-MRCT gives larger GR deviation than the individual test. So in future, we are going to study more real events and investigate when meta-MRCT is performing better than the other test and when it is not. So yeah, Thank you.
Great, thank you very much, Sakshi. Do we have any questions? You can feel free to raise your hand or use the question and answer box. But yes, please give some applause to Sakshi for her talk. Any questions? So while we're waiting, I have a quick question. So you used it, you actually compared, you tested your new test with the double neutron star, the famous double neutron star event. So can you test it with basically any of the mergers that have been detected by LIGO, Virgo, Kagra so far? And is the limitation purely signal to noise ratio?
So this is a very high signal to noise ratio signal. So it doesn't matter because we use like the same BBH fit, though it is a BNS signal. So we have like mapped over the all the parameter space to a two-dimensional space. So it doesn't really matter.
So you don't need really super high signal to noise ratio signals. Is that right? Is that what you mean?
Test, yes. So what happens in IMR-CT, there we split the signal. So we need comparable like SNRs, but here we don't.
Oh, I see. Okay. I don't see any other questions. So thank you very much, Sakshi, and we'll move on to the next speaker. So thank you very much. Great. Nicole Kusit, are you? I see Nicole is there. Let's check that you're visible and can unmute. I see you. Can you talk?
Yes. Can you hear me?
I can hear you. Yes.
Excellent.
So, all right. Perfect. All right. And while you're doing that, I'll introduce you. So we have Nicole Kusid, who's coming up to give this talk on strongly lensed supermassive black hole binaries as nanohertz gravitational wave sources. And Nicole is at Stony Brook University in New York in the US.
Yes. Thank you very much.
And I'll give you, if you're getting close,
up.
Yep. So you can go ahead and full screen that. And once you're getting close, if you're getting close on time, I'll mention something, but otherwise I'll just let you going. But basically it's 15 plus 5. All right.
Great. Awesome. All right. So hi, everyone. As Scott said, I am Nicole Kusid, and today I'll be talking to you guys about strongly lensed supermassive black hole binaries as nanohertz gravitational wave sources. So you can find this work on the archive, and it's been accepted for publication in AppJ. I will say, as a heads up, this was accepted for publication prior to the release of the 15-year results from Nanograv. So just a heads up for everyone. But yeah, let's get started. So this work is framed in future pulsar timing array capabilities. So particularly in the era of the square kilometer array. So the square kilometer array, or the SKA, is going to be a key player in the goal of detecting continuous nanohertz gravitational wave signals, especially from single sources. In the future, it's going to add a lot more pulsars to our pulsar timing arrays and significantly boost their sensitivities, achieving a minimum detectable strain of about 10 to the negative 16 in most of the PTA band, as you can see in the top right figure here. And especially in light of the new 15-year results from Nanograv, it's an especially exciting prospect to now think about targeted searches and detecting nanohertz gravitational wave signals from single sources, or presumably supermassive black hole binaries. So in the era of the SKA, we're going to get this great improved sensitivity. And I also have decided to look at how strong lensing can be used as an added bonus to further increase the reach of PTAs in the universe. So how does that work? Strong gravitational lensing basically just puts a magnifying glass on the whole universe. What this means for PTAs, similarly to how electromagnetic waves can be lensed and magnified by some foreground massive object like a galaxy or galaxy cluster by some magnification factor that I'll call mu, gravitational waves can be lensed in a similar manner, and their strains get amplified by the square root of that mu factor. And I demonstrate this happening in this bottom right figure on the slide, where you can see this 2D parameter space, redshift, and chirp mass of supermassive black hole binaries. And the white curves indicate that minimum threshold of a strain of 10 to the negative 16. And you see that space above the white curve gets broader and broader as we increase those magnification factors from 3 to 30 to 100. So it's already exciting that strong lensing can help increase the PTA detection volume. But on top of that, it opens up a lot of avenues for, for multi-messenger astrophysics with these strongly lensed sources. And I'll get into more of that later, but basically it comes down to novel ways of resolving electromagnetic counterparts and hopefully also resolving gravitational wave signals in different PTA frequency bands. So before I move on, I want to kind of motivate this a little further with an example. So let's imagine a typical supermassive black hole binary with a chirp mass of 10 to the 9 solar masses, a gravitational wave frequency of 1 nanohertz. So a binary system like this could be detected out to a redshift of about 0.25 if it's unlensed, along with some of the earlier detectable nanohertz gravitational wave signals from unlensed supermassive black hole binaries, which in our work we expect to begin detecting around a redshift of 0.2. If we now lens this system such that it's magnified by a magnification factor of 2, and for the gravitational wave strain, that means a factor of √2, it's now detectable out to a redshift of 0.3. And then if we jump to a magnification factor of 100, or for the gravitational wave strain, that's an amplification of a factor of 10, now the system's detectable out to a redshift of about 1.5. So as you can see, strong lensing is putting the unreachable within reach of PTAs for detection, and it can even put the system so far into reach that it could be amongst some of the earlier detected nanohertz gravitational wave signals from single sources, supermassive black hole binaries. So that's really cool. Like, this example is great, but what we really care about is, where are these things? Where are these systems? How large is this population of lensed sources? Where can we find them? So the main point of my work here was to build up this population of strongly lensed supermassive black hole binaries that are emitting detectable nanohertz gravitational waves in the era of the square kilometer array. So I start building this population with just a choice of mass function. So in this work, we use 2 examples. One's just a galaxy stellar mass function. The other is a quasar luminosity function. This one's important for us because we do have evidence for quasars signposting mergers. We apply a population cut with a binary fraction. We use a redshift evolving one here, and that brings us down to a population of specifically supermassive black hole binaries. And then we apply another population cut based on the probability for a source to be strongly lensed. And we take this probability from an SIS lens model, meaning a singular isothermal spherical lens model. This lens model results in, at most, double images of a background source. And it's a really good approximation for what's called an SIE lens model, or a singular isothermal ellipsoidal lens model, which can result in up to quadruply imaged background sources. And in future work, we'd like to go back and do this whole calculation with an SIE lens model. But for now, for proof of concept and simplicity's sake, we use the SIS lens model throughout this work. And then to make sure that we're correctly counting actually detectable sources of nanohertz gravitational waves, we perform a Monte Carlo in gravitational wave frequency and magnification. So we bin our 2D redshift and chirp mass parameter space up into small bins. In each of those bins, we are sampling over time to coalescence, which we're converting to gravitational wave frequency. We're also sampling over a magnification probability density function, which the one that we adopt, you can see on the right of the slide here. And armed with those two values, so the magnification factor and the gravitational wave frequency from Monte Carlo sampling, and then as well as the redshift and the chirp mass assigned to each bin. From there, we can calculate each bin's lensed strain. And for those bins whose lens strain surpasses that minimum threshold of 10 to the negative 16 minimum detectable strain in the SKA PTA, those bins are populated with those strongly lensed supermassive black hole binaries that we get from that population cut prescription that I had just described on the slide before. And so those strongly lensed supermassive black hole binaries in those detectable bins contribute to our total cumulative population count. And that is the main takeaway of this work. And that's what I'm showing you here. So you see the cumulative distribution of strongly lensed supermassive black hole binaries that are emitting detectable nanohertz gravitational wave signals out to a volume of redshift of 2. And so in this figure here, in purple, you see these results with that galaxy stellar mass function we discussed, and in teal for the quasar luminosity function, which we convert to a black hole mass function. And mu fixed refers to these wide bands, these pale wide bands that you see, which are composed of curves of fixed magnification. So that's for values ranging from mu equals 2 to mu equals 100, where instead of sampling over magnification, we assign a fixed magnification value to each bin, versus for the solid curves labeled mu integrated, those are the curves of integrated magnification, meaning that we do sample over that magnification PDF in each bin and extract that value for our calculations. And so we count within this volume about 800 detectable unlensed supermassive black hole binaries. On top of that, we expect an additional few and up to an additional 30 supermassive black hole binary sources emitting detectable gravitational waves, strictly due to the presence of strong lensing. And so to be consistent, we want to check how this underlying population of the unlensed binaries plus the population of additional binaries, with the maximum contribution being about 30 of those, how that combined population contributes to the gravitational wave background signal. And we compute a characteristic strain of about 2.05 times 10 to the negative 15 from our maximum contribution, which does fall within the range from the Nanograv 12.5-year data set, and now within the range for the 15-year data set as well. And so it's great. We have these sources. They're there. And we have this population of greater than one of these. Now, what can we learn from them? We know we'll be able to detect them in the future. What can we learn? So that's where the multi-messenger aspect comes into play. So let's first talk about electromagnetic counterparts. So strong lensing produces multiple images of a background source. In the case of a supermassive black hole binary emitting these detectable gravitational waves, if it's lensed by, say, a really massive elliptical foreground galaxy, there is the potential to resolve actually the individual orbiting black holes within an image of this lensed source. And so if you look at this figure, you see the orange hashed area corresponds to the best resolution with the NGVLA. So that's our best bet for being able to resolve these individual black holes this way. And actually, if you think about our example supermassive black hole binary that I used to motivate this work in the beginning of our talk, it would actually fall into this hatched orange NGVLA coverage area. So those black holes would be resolvable in an image of that background source. And even if we couldn't resolve those individual black holes, there's still probably lots of ease in resolving the discrete images of this background source. So we have multiple images. They're separated by an arc second or a few arc seconds. And these instruments here, so the NGVLA, the VLBA, the SK, this time as an imaging tool rather than as a PTA, they could all resolve these discrete images of the background source along with other instruments such as JWST and Athena, so across multiple wavelengths as well. So it's very exciting. Additionally, for high frequency supermassive black hole binary systems whose frequency evolution, gravitational wave frequency evolution rate is greater than or equal to 0.5 nanohertz per year, their multiply imaged gravitational wave signals could actually be resolved in different PTA frequency bins due to the time delays between these multiple images of the background source. And these time delays for the SIS lens model are on the order of about a year or a few years. So this introduces the possibility to do lots of tests of GR and, track the frequency evolution of this binary between its different images, which would be really interesting to see. So all in all, strongly lensed supermassive black hole binary sources are very intriguing candidates for very rich multi-messenger astrophysics. So just to summarize, we do expect an additional few and up to an additional 30 detectable supermassive black hole binaries strictly due to strong lensing, in addition to the unlensed binaries that we're set to detect. From our case study example, it's possible that such a source could be among some of the earlier detected gravitational wave signals from single sources, and this should motivate targeted searches. The NGVLA is probably our best bet for electromagnetic follow-ups of these sources, particularly for low frequency strongly lensed systems, and for high frequency strongly lensed systems, we can also hope to resolve the multiply image gravitational wave signals between different images of the lens supermassive black hole binary. So yeah, all in all, a very exciting prospect, and I'll take any questions. Thanks very much.
Great, thank you very much, Nicole. That was really nice. And applause from the audience. Yeah, so please use the question and answer box, or just raise your hand if you would like to ask a question. I don't see any right now, so I will ask one because I had a question about the golden binaries.
Yes.
So you mentioned the NGVLA is probably the best chance for that. And you probably said it, but I think I missed it. So for to do this plot, are you assuming the exact same magnification that you're getting from gravitational waves that you're going to get in the electromagnetic spectrum as well? And that's what's allowing you to actually do the resolving and the detection. Is that correct?
So that's almost the case. What happens is that, so let's say in this case, it's a magnification factor of 100 for the electromagnetic case. So for gravitational wave strain, that's a magnification factor of 10. And although it makes, in the electromagnetic case, although the strong lensing makes the source louder by a factor of 100, it amplifies the separation of the binary in the actual image by a slightly different factor, and that depends on the position of the background source with respect to the foreground lens. But that separation can be amplified by up to a factor of 60 in this case, when the magnification factor is 100. So we're using that factor of 60 here, but it can be anywhere between, I think at worst, a factor of 35, at most a factor of 60. But yes, that is what allows us to gain that extra strength in our resolution abilities.
Right. So because without the electromagnetic magnification, you would not be able to resolve those binaries, correct?
Right.
Yeah. All right. Great. Thank you very much for that. Other questions for Nicole? Oh, there's one in the question and answer. Nathan, would you like to ask that, or do you want me to just read it out? Happy to do it either way.
No, I can ask. So yeah, I was just wondering, so what sorts of pathogen are you thinking of? Just leading auto GW damping, or would you potentially have some sort of pressure coefficients or other things?
I haven't thought too deeply into the specific tests. Unfortunately for this work, it was mainly the idea just to, show the proof of concept that these sources do exist, and we can think about them more now that we know that they can be detectable. But particularly in the frequency evolution in these sources, if that F dot term does match, if what we expect with that F dot term does match what we do end up observing eventually. So that's the main thing that comes to mind, but there's plenty more to think about. We just haven't thought up specific priority tests for this work.
Okay, thanks.
All right, great. I think we're out of time and I don't see any more questions, so that's perfect. So thank you very much, Nicole. And thanks for all the other speakers, both in this little subsection, as well as the previous session about testing jar that we had right before this. So thank you all very much. And hopefully we'll see you in the next Amaldi sessions, which start in about just over 6 hours time. So take care, and we'll see you later. Bye.